Have you ever just, stopped to think about how fast your phone's calculator works? Or like how a massive supercomputer crunches numbers almost instantly?
It feels like magic sometimes, doesn't it?
Yeah.
But that speed, that instantaneous feel, it all comes down to some really fundamental principles of digital decision-making.
And that's exactly what we're diving into today. The magic behind it all. Combinational logic circuits. We've got this really comprehensive source material here. And our mission really is to unpack it all. We're going to look at what these circuits are, how they're different from other digital systems, what they're built from.
Right, the basic building blocks.
Exactly. And the common structures, how to actually figure out what one does if you see it.
The analysis part, yeah.
And just how vital they are. Pretty much every digital thing you touch uses them. Prepare for some aha moments, hopefully.
Let's jump in. So the core idea, the absolute defining characteristic of a combinational logic circuit is that its outputs depend only on the present inputs.
Only the
Exclusively.
Yeah.
That means they have no memory. Zero. They don't store anything about past inputs, and they're time independent, meaning no clock signal is needed for them to just do their job.
Okay, so it's like a direct mapping. Input changes, output changes instantly. Like flipping a switch, the light is on or off based only on the switch position right now?
Exactly that. A pure stateless mapping. You can picture it like a black box, right? It has n inputs coming in. And for every single one of the 2 to the power of n possible combinations of those inputs, there's one specific defined output. That direct, predictable link is what makes them so fundamental for quick decisions in digital systems.
Okay, that makes sense for combinational logic, instant stateless. But, my computer definitely remembers sides of RAM exists. Digital counters count up. How do those work? What's the big difference there? It sounds like more than just a technical detail.
No, it's absolutely fundamental. It's quite the biggest dividing line in digital design. The key difference is memory and state. Combinational circuits, memoryless. But sequential circuits, they're different. They have memory elements built in things like flip-flops.
Okay.
These elements store information, binary data, and that stored data is called the circuit's state. So a sequential circuit's output depends on the current inputs and its current state, its history.
Ah, so it remembers what happened before. That must make designing and analyzing them, well, a whole different ballgame.
Totally. And because they have state, they usually need time dependency. Sequential circuits are typically synchronized by a clock signal, controlling when the state changes. Combinational circuits, no clock needed, they're time independent. Structurally, sequential circuits also use feedback paths. The output from a memory element feeds back into the logic. Combinational circuits are strictly feed-forward. Data flows one way.
Input to output, no looping back.
Exactly. Think of it this way. Analyzing combinational logic is like looking at a static wiring diagram. It's purely spatial. Analyzing sequential logic, that involves time too. It's spatiotemporal. You're watching how things change over time.
It's still kind of amazing, though, that all this complexity, whether it remembers or not, is built from just a handful of basic things. Logic gates.
That's the foundation, the absolute primitives. AND or not.
The classics. NAND, NOR.
Right. And then XOR and XNOR. These are the basic operations. And, 1 usually means high GX voltage, 0 means low.
Standard stuff. But you mentioned universal gates. NAND and NOR.
Yes. This is a really powerful concept. NAND and NOR gates are called universal because you can build any other logic function using only NAND gates or only NOR gates.
Wait, seriously, any function just from one type of gate?
Seriously, think about manufacturing. If you only need to optimize and produce one type of gate really well, really cheaply, across a whole chip.
That's huge. Massive simplification. Cost savings. Wow.
It was revolutionary for chip fabrication.
Ah.
And then you have XOR, the exclusive OR. Its output is high H, only if the inputs are different.
The difference detector.
Exactly. And XMOR, exclusive NOR, is the opposite high H, only when inputs are the same.
So XOR's Boolean expression, that Q equals A prime B O R A B prime, that really spells out the different condition.
It does. And XOR has this other neat trick. It can act as a programmable inverter.
Programmable? How?
If you hold one input, HIGH, at 1, the output just inverts the other input. If you hold that control input LOW at 0, it acts like a simple buffer. The output follows the input.
Ah, so you can switch its function on the fly with a control signal?
Precisely. Which makes it super useful in things like arithmetic circuits, where you might need to invert or not invert a signal, depending on the operation. And of course, every gate has its symbol, its Boolean expression, and that crucial truth table.
Right, the truth table. lists every possible input combo and the resulting output. Indispensable for checking things.
Absolutely exhaustive.
Okay, so we have the basic gates. But complex systems aren't just millions of loose ANDs and ORs, right? They use bigger, predefined blocks.
Exactly. We move up a level to medium-scale integration, or MSI circuits. Think of them as standard reusable modules made from combinations of basic gates. They're like the common words or phrases in the language of digital design.
Okay, like prefab components, what kinds are there?
We can group them by function: computation, data routing, information translation, decision-making. Let's start with computation arithmetic circuits.
The most basic must be the half adder, right? Adds two single bits, A and B.
Yep. Gives you a sum output and a carry output. Like binary 1 plus 1 gives sum 0, carry 1. It uses an XOR for the sum and A and D for the carry.
But its limitation is it can't handle a carry coming in from a previous addition stage, can it?
Exactly, it's limitation. Which leads us directly to the full adder. It adds 3 bits, A, B, and a carry in.
Ah, okay, so they can be chained together.
Precisely. It produces a sum and a carry out.
Okay.
You cascade these, say, 4 of them, and you have a 4-bit adder. And, need bit of design hierarchy, you can actually build a full adder from 2 half adders and an OR gate.
Cool, so that's computation. What about moving data around? Data routing.
That's where data routing circuits are key. First up is the multiplexer, or NUX. People often call it a data selector.
Selector.
Yeah. It takes several input lines, maybe 2, 4, 8, 2 to the end lines, and selects one of them to route to a single output line, which when it selects is controlled by N select lines.
Like a digital rotary switch, choosing one channel.
Good analogy.
Yeah.
Super important for picking which data source goes where, like choosing which register feeds the main processing unit, the ALU.
Right.
It can also convert parallel data lines into a single serial stream.
Okay. And if there's a selector, there's probably a distributor.
You got it. The demultiplexer, or DMUX, it's the inverse. Takes a single input line and routes it to one of 2 to bin possible output lines, again chosen by N select lines.
So MUX funnels things in, DMUX sends things out to specific places.
Exactly. Like sending data to one specific memory chip or output device, it basically converts a serial stream back into parallel paths.
Makes sense. They manage the data traffic. What about when data needs translating? Different codes, maybe.
That's the job of code conversion circuits. An encoder takes many input lines, usually assuming only one is active, and converts that active line into a compact binary code on fewer output lines.
Like on a keyboard. Press one key, it generates a specific code.
Perfect example. Now, if multiple inputs could be active, a simple encoder gets confused. So you have priority encoders that know which input has the highest priority if several are active at once, and only encode that one.
Ah, handles conflicts. Clever. And the reverse.
The decoder does the opposite. Takes an n-bit binary code as input and activates only 1 out of 2 to the n output lines.
So if you put in binary 101, maybe output line 5 goes active and all others stay inactive.
Precisely. Critical for things like memory address decoding, taking the binary address from the CPU and activating the exact memory location needed. Decoders are also powerful because they can act as min-term generators, essentially giving you a way to implement any Boolean function directly.
Okay, one more category. Decision-making. Comparing things.
Right, comparison circuits. The main one is the magnitude comparator. It takes 2 n-bit binary numbers, A and B, and tells you how they relate.
Like, is A bigger than B smaller, or are they equal?
Exactly, those 3 outputs, A, B, A, B, A, B. Equality is usually checked bit by bit using XNOR gates. Greater or less than involves comparing bits starting from the most significant bit MSB down to the least significant LSB. Importantly, this comparison happens in parallel for all bits, so the result is basically instantaneous.
Okay, so we've covered the basics, the building blocks, these MSI structures, but let's say I find a diagram of a combinational circuit I've never seen. How do I actually figure out what it does? How do I analyze it?
Great question. That's where the systematic combinational circuit analysis process comes in. The goal is to take the physical diagram, the structure, and derive its function, what it actually computes.
So going from the wires and gates to understanding its behavior, how do we start?
Step 1. Circuit deconstruction. First, clearly identify and label all the external inputs and the final outputs. Then, and this is crucial, label the output of every single gate inside the circuit with a unique intermediate variable, T1, T2, P1, Q3, whatever.
Break it down into smaller pieces, label everything, creates a map.
Exactly, it gives you points of reference. Step 2, deriving Boolean expressions. Now you work from the inputs forward. For each gate, Write down the Boolean expression for its output using its inputs, which might be the primary inputs or those intermediate variables you just labeled.
Okay, so T1 might be A, and D, B, T2 might be C, O, R, D.
Precisely. You keep doing this, substituting the expressions for the intermediate variables as you go, until the expression for each final output is written only in terms of the original primary input variables, like A, B, C, etc.
So you end up with a big algebraic equation for each output, based only on the inputs.
That's the goal. That equation is the function of the circuit.
Got it. Then what?
Yeah.
Use that equation.
Step 3. Constructing the truth table. Now that you have the final Boolean expression, you build the truth table. Columns for all inputs, columns for all final outputs.
Yeah.
If you have m inputs, you'll need 2m rows to cover every single possible input combination.
List all possibilities. 1000, 0, 1, 0, 10.
Yep. Then, for each input row, you plug those n zeros and ones into your final Boolean expression and calculate the output value. Put those in the output columns.
Okay. You could also add columns for those intermediate T1, T2 variables to make the calculation easier row by row, right?
Absolutely. It helps break down the calculation and avoid errors. Very useful for more complex expressions.
Now, that expression we derived first, it might not be the simplest way to represent that function, could it? It might use more gates than necessary.
Often it's not the simplest. That brings us to step 4. Logic simplification and optimization. This is vital. A simpler circuit is cheaper, uses less power, and is usually faster because signals have less logic to travel through smaller propagation delay.
Makes sense. How do we simplify?
2 main ways. First, using Boolean algebra. You systematically apply all those laws and theorems, identity, distributive, De Morgan's, absorption, etc., to manipulate the expression into a simpler form. This takes practice and recognizing the patterns.
Okay, the algebraic muscle approach. What's the other way?
The more graphical, often more systematic way, especially for up to, say, 5 variables, is using Carnot maps or K-maps.
Ah, yes, K-maps. The grids, how do they work again?
You create a grid with 2 n cells. The absolute key is labeling the rows and columns using gray code.
Where only one bit changes between adjacent labels.
Critical. That ensures adjacent cells in the map represent input combinations that differ by only one variable. Then, you plot the ones from your truth table onto the map. The simplification comes from grouping adjacent ones.
And the rules for grouping?
Groups must be rectangular. They must contain a number of cells that's a power of 2, 1, 2, 4, 8, etc. You aim for the largest possible groups to cover all the ones. Groups can wrap around the edges of the map top to bottom, left to right, and cells can be part of multiple groups.
Okay, cover all the ones with the biggest possible power of 2 rectangles, allowing wraparound. What about don't cares?
Don't care conditions, marked X. You can include them in a group to make the group larger, but you don't have to cover them. They're wildcards for optimization.
Once you have the groups, how do you get the simplified expression?
For each group, you look at the input variables. If a variable's value stays the same across all cells within that group, always 0 or always 1, you keep it. If a variable changes within the group, is both 0 and 1, you eliminate it. You combine the terms from each group with ORs.
Right. Variables that are constant within a big group define that simplified term. Okay, makes sense. What's the final step?
Step 5. Verifying the output. Crucial. You take your simplified expression, the one you got from algebra or the K-map, and you create a brand new truth table just for it.
Okay.
Then you compare this new truth table, row by row, output by output, with the truth table you made for the original unsimplified circuit. If the output columns match perfectly for all input combinations,
then your simplification is correct.
Exactly. The analysis is complete, and you know the function, and you have an optimized version. You can then draw a new, simpler logic diagram based on that simplified expression.
Let's try a quick example, say 3 inputs A, B, C, 1 output F, maybe some A and D's and ORs jumbled together.
Okay. Steps 1 and 2. Let's say we trace it out and find the unsimplified expression is F, A and D, B or R, B or C, and E, C. We label intermediate points, maybe T1 to T2 equals B plus C, T3 T2 A and D, C. So F equals T1 plus T2.
No, I didn't. F equals AB plus B plus CC. For step 3, the truth table, we list 0, 0, 0, 0, 0 to 111 for ABC. If we plug those into F, AB plus B plus CC, let's say we find F is 1 for inputs 0, 0, 1, 0, 11, 101, 110, and 111. Those are the midterms where the output is high.
Right. Now, step 4, simplification. Using Boolean algebra on F equals AB plus B plus CC. Distribute the C, F, AB plus BC plus C.
Okay, and CC is just C, right? Idempotent law.
Yeah, so F is simply plus BC plus C. Now look at BC plus C. That's the absorption law. C absorbs BC.
So BC plus C simplifies down to just C.
Exactly. So the whole expression simplifies beautifully to FAB plus C.
Wow, that's much cleaner than AB plus B plus CC. How would the K-map look for this?
Would plot those ones for minterms 1, 3, 5, 6, 7 on a 3-variable K-map, labeled with gray code, of course.
Right.
You'd see a nice block of 4 ones covering 1, 3, 5, 7. In that block, A and B change, but C is always 1. So that group gives us the term C.
Yeah.
Then you've got minterms 6 and 7 left. They form a group of 2. In that group, C changes, but A is always 1 and B is always 1. So that group gives us AB.
And putting them together, COR-AB, F equals AB plus C. Same result.
Exactly the same. Both methods get you there. And for step 5, verification, you'd quickly make a truth table for F, AB plus C and see it matches the original one perfectly. The original circuit might have used, say, 5 gates. The simplified F, AB plus C needs only 2. One A and D gate for AB, one OR gate to combine it with C.
That really drives home the point of simplification. Fewer gates, faster, cheaper.
That's the goal.
And this whole process really shows how analysis and design are like two sides of the same coin.
Absolutely. They're inverse processes, totally linked. Analysis is deduction. You start with a circuit diagram and figure out, what does this do? You derive the function, the truth table. It's like forward engineering.
Deciphering the blueprint.
Right. And design, or synthesis, is creation. Start with a need. I need a circuit that does this function, described by requirements or a truth table. And you figure out, how do I build the best circuit for that? You create the optimized diagram. That's kind of the reverse engineering aspect.
Starting with the function and building the form. And you use the same tools, Boolean algebra, K-maps, just working in opposite directions.
Exactly. A good digital engineer needs to be comfortable moving both ways.
Now, doing this by hand, K-maps and algebra, it's essential for understanding. But for real-world complex stuff, engineers use software tools, right?
Oh, absolutely. Manual analysis is fundamental for learning, but modern design relies heavily on software. For education, graphical simulators like Logisim are fantastic.
Logisim, what's that like?
It's free, open source, very intuitive. Drag and drop gates, connect them with wires. It does live simulations, so you can flip input switches and see the zeros and ones change on the wires in real time.
Oh, cool. Instant feedback.
Yeah, and it supports hierarchical design. Plus, it has this amazing combinational analysis tool. You can give it a truth table, it derives the Boolean expression and draws the circuit. Or give it a circuit, it gives you the table and expression. Or give it the expression. You get the idea. It converts between all 3 representations automatically.
Wow, that sounds like a perfect learning tool. Bridging theory and practice?
It really is. But in the professional world, especially for designing chips like microprocessors or using FPGAs, field programmable gate arrays, drawing huge schematics isn't feasible.
Too many millions of gates.
Exactly.
What?
So engineers use hardware description languages, HDLs. The 2 big ones are Verilog and VHDL.
So they describe the hardware using text, like programming code.
Pretty much. They write code that describes the circuit's structure and behavior, often at a higher level of abstraction than individual gates. Then, powerful software tools called synthesizers take that HDL code and automatically generate an optimized gate-level implementation.
The software does the K-map work, essentially, but on a massive scale.
On a massive scale, yes. An HDL design allows for creating sophisticated simulation environments called test benches. You write more HDL code just to test your design thoroughly, simulating inputs and checking outputs, long before you commit to expensive physical hardware.
Okay, so we have the theory, the tools, but we should also touch on the fact that real circuits aren't quite the perfect, instantaneous things we model on paper, right? There are physical realities.
Very important point. The ideal model is just that, an idealization. Real circuits have physical limitations. And even before we get to physics, simple mistakes happen in analysis.
Like what kind of mistakes?
Oh, basic stuff. Logical and assignment errors, misinterpreting what a gate does, connecting a wire to the wrong input. Happens all the time if you're not careful. Boolean algebra errors, applying a law incorrectly, especially things like De Morgan's theorems, or just messing up the order of operations.
And those K-map errors seem easy to make too.
Definitely. The biggest K-map killer is forgetting to label rows and columns in gray code order. If you don't do that, the whole adjacency principle breaks down, and your groupings will be wrong.
Ah, fatal flaw.
Totally. Also, making groups that aren't power of 2 sized, not finding the absolute largest possible groups, forgetting that the map wraps around, or misusing don't care terms like trying to group only X's together, which you shouldn't do, all lead to bad results.
Okay, so those are human errors. What about the physics? You mentioned propagation delay.
Right. In the real world, it takes a tiny but non-zero amount of time for a change at a gate's input to actually cause a change at its output.
Right.
That's propagation delay. Gates aren't infinitely fast.
And this delay can cause problems.
It can lead to something called hazards. These are temporary, unwanted glitches or spikes on a circuit's output. They happen because signals traveling through different paths in the circuit might have different total propagation delays.
So signals arrive at different times, even if they started from the same input change.
Exactly. And that timing difference can cause a momentary incorrect output value before the circuit settles down to the correct state.
Can you give an example?
Sure. Think about the simple function f equals a or a
Right.
prime. Algebraically, that should always be 1, right?
Yeah, A is either 1 or 0. If A is 1, F is 1. If A is 0, A prime is 1, so F is 1, always 1.
Correct. But build it with real gates. You have A going into an OR gate. You also have A going into a not T gate. And the output of the not T gate A prime going into the same OR gate. Now, imagine A switches from 1 down to 0.
Okay.
A itself goes to 0 immediately at the OR gate input. But the not T gate has a small propagation delay. So for a tiny moment, the output of the not T gate might still be 0, the old value of A prime, even though its input is now 0.
Ah, so for a split second, both inputs to the OR gate could be 0.
Exactly. And if both inputs are 0, the OR gate's output momentarily glitches down to 0 before the NOT gate catches up, A prime becomes 1, and the OR gate output goes back up to the correct value of 1.
Wow. So the output that should have stayed steady at 1 dipped down to 0 for a moment.
That's called a static 1 hazard. Static because the output should have stayed static at 1. There are also static 0 hazards and dynamic hazards where an output that should change cleanly once might flicker multiple times.
And these glitches could actually cause errors in a larger system.
In fast systems, absolutely.
Yeah.
A downstream circuit might read that momentary glitch as a valid signal. Designing hazard-free circuits involves more advanced techniques, often adding redundant logic, but it highlights that purely logical analysis isn't the whole story. Timing matters.
It's incredible, though, that despite these potential issues, these combinational circuits are just everywhere. They're the workhorses inside pretty much every digital device we use.
They are absolutely indispensable. Think about the processor, the CPU in your computer or phone. The arithmetic logic unit, ALU, is the core part that does calculations and logic operations.
Adding, subtracting, ANDing, ORing.
All that. It's built almost entirely from combinational logic circuits. Adders, subtractors, gates for bitwise stuff, comparators for decision-making and branching. All combinational.
And getting data to and from memory.
When the CPU wants to read or write memory, it puts a binary address on the address bus. An address decoder, a classic combinational circuit, takes that address and activates one specific memory location out of millions or billions. Purely combinational.
Pointing to the right spot.
Exactly. And inside the processor itself, managing where data flows. That's often done by multiplexers.
The data selectors we talked about.
Yep, selecting which register's value goes into the ALU, or whether the data comes from memory or a calculation result. MUXs are constantly directing traffic, ensuring the right data is processed at the right time. All combinational logic.
And it's not just CPUs and memory, is it? It's broader.
Oh yeah, encoders in your keyboard, turning key presses into codes. Decoders driving the segments of digital displays on clocks or appliances. MUXs and DMUXs managing data streams in network routers and communication systems. Combinational logic doing error checking on data transmissions. It's truly fundamental.
Wow. So we've really gone from the basic idea of instantaneous logic to seeing how it forms these complex building blocks and powers basically everything digital around us.
We've covered the core concept, the gates, the MSI structures like adders and MUXs, the whole analysis process, deconstruction, expressions, truth tables, simplification with algebra and K-maps, verification.
And looked at the tools like Logisim and HDLs, the real-world issues like hazards, and finally, where these things actually live in ALUs, decoders, everywhere.
So next time you tap your phone or your computer does a calculation, remember those billions of tiny, near-instantaneous decisions being made by combinational logic circuits. You now have a bit of a mental shortcut to understanding the logic behind it all.
It really shows how complexity emerges from relatively simple rules and components. It kind of makes you wonder, doesn't it? What other seemingly basic fundamental building blocks might be out there, quietly running the complex systems we rely on every day, just waiting to be understood?
It's a great question. And if this has piqued your interest, definitely try playing around with a tool like Logisim. Get your hands dirty building some circuits, or check out some of the excellent textbooks and online resources on digital logic design for an even deeper exploration.